Now in process industry, the meaning of aggressive environments is with respect to the material, with respect to internal and external atmosphere, environmental conditions, the fluid which is passing through the pipes, okay, and the process conditions. So with respect to all these factors, we define it as an aggressive environment. So metallurgical tests, as we have discussed, these tests are required to check the integrity of materials with respect to all the ASTM standards, right? We check the composition required, what kind of corrosion may happen, what kind of defects are there. All these factors we need to identify. So this is the purpose of performing metallurgical tests. Now we have 5 categories here. One is grain size testing, second is intergranular corrosion test, ferrite test, then hydrogen induced cracking test, sulfide stress corrosion cracking test. So these are the 5 type of testing which we perform to identify various kind of defects in various materials which are generally used in process industry. So now we'll try to understand the basic fundamentals behind each and every test. In process industry, we generally use different materials, right? At the same time, we have a lot of American Society of Testing Material Standards which define 2 things. One, the chemical requirements, chemical properties, chemical composition of the material. Second, the various type of tests which are required. Okay, so when we are using different materials, we have to understand the metallurgical tests which are there, which we need to perform to identify the defects and to rectify the solutions. Okay, so there are few tests which we need to understand, which we are going to discuss here. Majorly we divide it into 2 categories. One is micro and macro. Okay, now in under micro section, we need to understand the raw material for which we are going to use that pipe or any other material, or what kind of product it is, and weld. Okay, so that in the end we need to ensure that all the alloying elements which are there available in the material are within the range which is specified in the specific material standard. So that is the first and topmost agenda in any micro analysis or chemical analysis, right? In the micro analysis, for welds, we need to check the proper fusion of weld materials. Okay, so that is the second topmost agenda under macro analysis. So these are the 2 type of metallurgical tests broadly we are using in the process industry. Grain test is one of the tests which we perform, which comes under metallurgical testing, which are generally performed during aggressive environments. Okay, so in this section, what we are going to understand is what is grain size, why it is important, what are the various factors which impact the grain size, what are the various ASTM and ISO standards which are talking about the grain test, then basics about grain test, how we perform it, what are the various things which we consider while performing this test. Then along with that, we'll try to understand few of the important factors, important facts related to grain test. So this is the total agenda which we are going to cover in this particular section. Now let us try to understand the problem statement, why we are discussing this grain size, why it is important, right? If you look at the various shipments related to tubes, sometimes what happens, there is a poor surface finish. Okay, we can easily see the orange peel that is available on the surface of the pipe which we receive in the shipment. From one load to next, we check all the dimensions are within the limit which are specified in the ASTM standards. All those have passed through all the quality checks, but still there is some problem, right? Everything is within the acceptable limits, but still these are not acceptable. Why? Because orange peel appearance is there. Now what is that? This is nothing but these are the improper grain sizes which are available in the material of the pipe, right? So to achieve a balance between grain size and mechanical properties, okay, the proper process planning is critical. Now the manufacturer has to go through a lot of things to create a balance between grain size and mechanical properties, right? A lot of mechanical properties are there which we are defining in the purchase order and the manufacturer has to fulfill. So a lot of time and energy is required to reach up to the balanced condition where all the grain size and mechanical properties are met as per the requirements. But at the same time, sometimes the manufacturer has a pressure of delivery. They don't have much time to invest, so sometimes this grain size factor is ignored, right? This is the last thing which manufacturer considers. I'm not saying they ignore it, but as compared to other mechanical properties which are defined in the written format, this is sometimes ignored. So this is a rarely is a top priority for any data compilation, right? So this is the basic reason that we get imbalance between mechanical properties because of grain size. Now to understand what is grain size and what is the impact of grain size, okay, we need to really look into the material surface. If we zoom it to 50x or 100x magnification, we can see such kind of grains. This is a very good picture which I have taken from Wikipedia. These are the grains. If you look at these and the boundaries, so we can easily visualize how these grains are associated with each other within the material, right? So the size of these particular item will be defining the mechanical properties of any material, right? So we'll try to understand how this is impacting the material properties, but first we need to visualize what we are talking about. These are the grains. Grain sizes are different, there are grain boundaries in between. So this is how material is made up of a lot of grains. So grain size of a metal or a single phase alloy is an estimate of an average grain diameter, okay, and it is generally expressed in millimeters. Now if the grain size is decreasing, the metal becomes more stronger in the sense it becomes more resistant to the plastic flow, okay. So that means we are getting the better mechanical properties, nothing else. As the grain size increases, the opposite effect on strength occurs. That means it decreases the strength, it decreases the resistance towards the plastic flow. So if you look at here, when the size is more, the grain boundaries are different. If the sizes are smaller, the grain boundaries are different. So in a particular volume, the number of grains are different with respect to the size. So now we need to understand, when the size is increasing, the number of actual grains in a particular volume, that will decrease, right? That means total area of grain boundary is reduced. Now this is related to the strength of material, mechanical properties of the material. For a number of products such as heavy wall pipes, if you talk about very thick wall pipes, then this grain size is not having much impact. But as the size is decreasing, the thickness is decreasing, this grain size is having a comparatively high impact, right? In comparison, if we compare two pipes with identical dimensions and wall thickness, the one with finer grains has more grains, right? More grains means it is contributing to the additional ability which can withstand the internal pressure. In other words, when all the other factors are held constant, finer grains makes a stronger metal, right? So this is something which we need to understand, what are grain sizes and how the grain boundaries, grain volume, how this is impacting the mechanical properties of the metal. If you look at various factors that affect the grain size, okay, which will indirectly impact the mechanical properties of any material. So basically we can divide it into three parts to understand the impact of change in grain size on change in mechanical properties. So first one is alloy chemistry. second is cold work, right? Annealing process. So we'll discuss all these three processes so that we can understand the impact on grain sizes. At the same time, let us look at this diagram. This is the mechanical property axis. In this we are increasing the grain sizes. So if you look at these curves, these are representing the strength. That means as the grain sizes are increasing this way, the strength is decreasing, ductility is increasing. Okay, this we can understand when we look at the next slide, where we'll discuss the cold work done on the material. Then again the toughness is also decreasing as the grain size is increasing. So this is how this grain size is important, how it is impacting on the mechanical properties. Now for example, if we talk about the alloy chemistry and the impact on grain size, there are few examples such as titanium and niobium. Okay, few alloys will be having these elements in certain percentage, which is defined in the various ASTM standards, which may trigger the grain growth in stainless steel. Okay, so that means this is just a property of these elements. If it is there, it will trigger the grain growth in stainless steel. At the same time, for some stainless steels, lower carbon content does the opposite, right? That means these two elements are triggering the grain growth. Carbon is reducing that grain growth. So this is just a property of these elements, which if available in the steel, they will have impact on the grain size. So this is why we are calling it alloy steel, alloy chemistry, because we have few elements which have their own properties and they have their own impact on the grain sizes. So once the grain growth is there, okay, these properties are decreasing. Once the carbon is there, this will be having the opposite impact. So strength will be increasing, toughness will be increasing, but at the same time ductility will be increasing if the carbon content is low. Now to understand the impact of cold work and annealing temperature on grain size and the mechanical properties, we have to look at this diagram. If you look at this section, right here, what is happening, we are doing a heavily cold working in this part of the material. That means at the time of heavily cold work, these grain sides will be elongated. Okay, this kind of structure change will be there. At the same time, if we start looking at the second part here, right, when we are doing the cold work, there will be a lot of residual stress will be there, right, at the boundaries, so that we have to perform the annealing process to release these stresses. Now what we are doing here in this part, where there is a change in crystallization, like the structural change of the grain, what is happening when we are doing a moderate amount of annealing, right, within the temperature limits and within the time period specified in various standards. If we are performing the moderate annealing, then the elongation will be coming back to their original sizes. This will be recovered and new grains will be formed, smaller grains will be formed. That means more grains will be available within the particular volume, right? If we keep on doing the annealing, we don't stop at particular time period, we keep on doing the annealing, then the grain sizes again start increasing. Okay, so this is how there is a change in grain sizes when we are doing a cold work, when we are doing annealing within a particular time period and range. If we keep on doing that annealing for a longer period, then there is a change in grain sizes. At the same time, if you look at the strength, hardness and ductility, okay, this will keep on increasing, this is keep on decreasing, this is keep on decreasing, right? So this is how at this point, if you look at, there is a lot of internal residual stresses. So once we start annealing, this will keep on decreasing. So this is how there is a change in grain sizes, there is a change in mechanical properties with respect to grain sizes, and there this is how we can understand the impact on various materials with respect to grain size. Now grain size is really important in metallurgical testing. So there are few ASTM standard and ISO standards. ASTM E112, ISO 643. These two standards are generally used to perform this grain size testing, right? So what is the basic criteria there? If you talk about E112, right, they have defined a scale from G00 to G14, right, and they are defining the grain sizes between 2.8 to 500 range. Okay, if you look at this microstructure, if you zoom it to 100x, okay, then we can identify such structures on metallographer, which is used to evaluate the microstructure. So first step is we have to magnify the surface up to 100x, then we can see these kind of structures there. Then we will relate these pictures, these material structures, surface pictures, with respect to the pictures given in the ASTM E112, right? Once we compare these structures with respect to the pictures given in ASTM, we will evaluate the range of grain size, right? The relevant standard provide guidance in assigning the grain size. Automated grain size measurement has become common, thus removing any guesswork from the process. So ASTM 3E112 is used to identify the relevant grain size. Okay, there are grain size number, ASTM numbers are given, which are, as the number is increasing, the grain size is decreasing. So once we select one of the pictures given in this, the number will be associated there. So with respect to that, we can calculate the size, whether it is mm or inches. So once we know the ASTM number, we can identify the size. So this is how ASTM standard is helping us to identify the size of grain. So once the grain size is identified, we can check with respect to various standards whether we are going to accept that material or not, or whether we need to perform any heat treatment to refine the grain sizes or not. So that will be the starting point to identify the further processes. So this is how these standards are helping us in grain size testing. Once with the help of ASTM standard we identify the ASTM number, right, we know what is the size. Now there are few things which we need to remember. Grain size usually is specified by the product engineer and is based on the application and wall thickness. Okay, various wall thicknesses will be having different kind of structure and various resemblance with respect to ASTM standard. For walls 0.050 inch and thicker, okay, grain size 5 is usually acceptable. So this acceptance criteria is also defined in ASTM standard. So when the sizes are up to this range and above, the grain size 5 is acceptable. For wall sizes around this inch size, grain size up to 6 is acceptable. So this kind of range is also available, so that we can check the sizes and we can provide our acceptance or rejection with respect to the requirements. For even smaller sizes around this much 0.005 inch, a grain size 7 or finer is required. So this is required, that means if it is not, this condition is not met, we can always reject the material. In general, as the wall thickness gets lighter, the need for finer grain size increases. As we discussed, if the material, the wall thickness is very high, then this grain size is not having much impact. Once the size is becoming, the wall thickness is becoming less, it is becoming thinner, then the grain sizes plays a really important role. So this is how we can associate the grain size is ASTM number with respect to ASTM standard, and we can identify the acceptance and rejection criteria, and we can define the mechanical or chemical properties. Intergranular corrosion testing. In process industry, this is again one of the aggressive environments where we have requirement of such testing. So in this section, what we are going to cover is we'll try to understand what is intergranular corrosion, how we can avoid this kind of corrosions, what are the various industry standards, testing standards which are generally used to identify such type of corrosions. Then we'll just have a look at 5 various acid tests which are really very popular to identify, to perform these testings. So let us start with the understanding the intergranular corrosion section. Now let us try to understand what is intergranular corrosion and why it happens and where it happens. Okay, so mostly we see this kind of corrosion in stainless steels at the grain boundaries, right? Why it happens? It is result of chromium depletion, right? Because it happens mainly due to the precipitation of chromium carbides in the grain boundaries. So let us look at why it happens, why these chromium carbides precipitation is there, especially in stainless steels. If you look at the chromium carbides can be precipitated if the stainless steel is sensitized in the temperature range of 550 to 850 degrees Celsius. Okay, so if you look at when this happens, this may happen at the time of welding, or it may happen at the time of heat treatment processes. So stainless steel may see this temperature range even we are not asking, we are not designing for such high temperatures. At the time of welding and heat treatment, these temperatures may be there. So at that time the chromium carbide formation may happen. If the temperature lies in the critical range for too long, okay, if this temperature range comes only for momentarily very a short period, then it is okay, it doesn't happen. But if it is there for a longer period, then chromium carbides will start to form in the grain boundaries, okay, then which is susceptible to the intergranular corrosion. The area adjacent to the grain boundary becomes depleted in chromium, right? The chromium reacts with carbon and forms carbides around this zone, therefore becomes less resistant to intergranular corrosion. So this is nothing but precipitation of chromium carbides at the grain boundaries when the stainless steel goes through this kind of temperature range, and this generally happens at the time of welding or heat treatment. So this is how this is something about intergranular corrosion. Now when we are using stainless steel, we know there may be chances of intergranular corrosion at the grain boundaries. So there must be some options, some ways of payouts to minimize the scenario. So what are the various options how we can minimize this intergranular corrosion? First thing is, we have found that materials where the carbon content is less than 0.05 normally have sufficient resistance. Okay, why this scenario is there? If you look at, we have extra low carbon content steels where we have limited the carbon content up to 0.03%, right? We are talking about 0.05, where below that the material shows some resistance towards intergranular. Considering this factor, we have a category of low carbon steel where we limit the carbon content up to this much. That means we are not allowing the chromium to react with carbon to form chromium carbides. If there is lesser carbon, there are lesser chances of formation of chromium carbides at the grain boundaries, right? So this limiting the carbon is one of the factors which can reduce, which can minimize the intergranular corrosion. Another option which is really found good to minimize this intergranular corrosion is introducing the titanium or niobium elements. The nature of these elements is like if these elements are there in any of the stainless steels, then instead of forming chromium carbides, there will be formation of titanium carbides, right, which will not decrease the chromium content. If carbon is high and there are chances of formation of chromium carbides, then we introduce these two elements which will lead to the formation of titanium carbides instead of chromium carbides. So the resistance toward corrosion will be high, and resistance intergranular corrosion will be lesser, right? So this is how we can minimize the intergranular corrosion in stainless steels. If we talk about ASTM standards and guidelines regarding intergranular corrosion testing, we need to understand few things. Okay, ASTM 262 is one of the ASTM standard which is globally recognized and used, right, for intergranular testing. The methods are given in this standard so that we can quickly screen the batches of material to determine corrosion susceptibility. Right, how we are doing this? There are 5 unique tests which are defined in this ASTM standard. We need to select the correct method based on the understanding of the material and processes, right, as well as the concept of corrosion itself. We need to understand the material, various processes, the corrosion itself, so that we can decide which out of these 5 tests we need to select to perform the test, right? These tests are really very popular because of its relatively short turnaround time to identify to get the results, right? We can have the specimen inserted into the acids. These 5 methods have different 5 acid tests. We can choose one of those and we can insert the specimen into that particular acid, and we can keep it there for particular time duration. Once we are done with the insertion for a particular time period, we can conclude of the test by measuring the weight loss, or we can identify it visually also, right? So this is something which is defined in the ASTM 262. Now let us look at these 5 tests, how and what acids are used, what is the basic criteria. This is a summary of 5 tests which are given in ASTM 262 to identify the intergranular corrosion testing. Now these are the test types. If you look at, these are the 5 tests, and these are the acids which we are using to perform these tests. Okay, so each acid has its own properties with respect to material. Based on experience, we have to select which material, which acid we have to combine. So let us see what is happening here. The first test, which is oxalic acid test, which is quickly screening the material. That means we can quickly check whether it is acceptable, or we are expecting some kind of corrosion in it. Okay, so this is applicable to corrosion associated with the chromium carbide precipitates, right? So this is one of the tests. If you look at the second test, that is ferric sulfate sulfuric acid test, here what we are doing, when we are inserting the specimen inside the acid, we have to keep it there for 24 to 120 hours, and we have to evaluate the results. The level of corrosion is determined by the mass loss, right? And we perform this type of test for stainless steel and nickel alloys. Okay, so we know what is the test, what is the acid, and how long we are keeping the specimen inside it. Okay, and how much is the weight loss, and where we are using it. Now third test is for nitric acid solution, where we are using nitric acid as a acid in this test. Again we are keeping it to 48 hours, Okay, 5 48-hour intervals. The specimen will be inserted inside it and it will be kept there for 48 hours, then again 48 hours, then again it will be repeated for 5 times. This kind of test we are performing where chromium depletions and corrosion in intermetallic phases, right? So this is where we are using it. Again we are having copper sulfate sulfuric acid test, right, where we are boiling the specimen for 15 hours. Okay, we are using a mixture copper sulfate sulfuric acid. This is a mixture and we are using it for 15 hours. Again we are using, where this is applicable, areas high in chromium carbide formations. This is the application where we are having this type of test. Then the fifth one is copper sulfate test, where we are keeping the specimen for 28 hours, boiling test. Then application is stainless steel and low carbon steel. So ASTM 262 defines these 5 tests where we are keeping the specimen for particular time range, and these are the applicable materials which are used for with respect to these respective acids. So in this section we have covered the intergranular corrosion testing, try to understand the concept, what it is and how to avoid this type of corrosion, what are the various ASTM standards, and what are the various acid tests available to identify the intergranular corrosions. So agenda, what we are going to cover in ferrite testing is like what is ferrite testing, first topic. Then we'll try to understand the importance of ferrite testing, then impact of ferrite content, how to perform this ferrite test. So these 4 topics we are going to cover in this video. So let us first try to understand what is ferrite testing. It is nothing but a technique to measure the delta ferrite which is available in any of the austenitic stainless steel or duplex stainless steel. We need to measure how much content of ferrite is there, right? This is one of the non-destructive testing. Now why it is important, there are few things which are important in process industry. We need to understand the mechanical properties of steel, we need to understand the weldability, we need to understand the corrosion resistance. Based on these things we decide any uses, any application of the steel. So if we know the ferrite content, we can easily decide how much is the impact. Right, now let us look at the content. If it is too high, then there may be different impact. If it is too low, then it can be a different thing. So let us see, if it is too low, right, then stainless steel may be susceptible to solidification cracking, because we are going to do some welding, there will be different temperature zones. So at particular time there may be hot cracking if the content of ferrite is too low. At the same time, if it is too high, then there is a risk of corrosion increases, right? Also, the mechanical properties of stainless steel could be negatively affected if ferrite content is too high, right? So we really need to measure how much is the ferrite content in stainless steel, austenitic stainless steel and duplex stainless steel, because this is going to have impact on the properties of the metal. Now let us look quickly at how this ferrite content is measured. There will be uses of probe, right, which is placed on the material being investigated. Then closed magnetic circuit will be there, which is going to measure the content. It will be displayed digitally, right? So we can easily measure the content of ferrite in any particular location. Okay, in austenitic stainless steel, 4 to 8% of ferrite is acceptable, right? It is not going to impact on mechanical properties or weldability if it is within the range of 4 to 8%. At the same time, in duplex stainless steel, these 35 to 65 ferrite is preferred. Mostly 50% is optimum, right? So these are the properties which need to be there so that we ensure corrosion resistance, toughness and strength. So in this video we try to understand what is ferrite testing, importance of ferrite testing, impact of ferrite content and how to perform the test. And we try to understand what is the percentage of ferrite which is acceptable in austenitic stainless steel, and alloy steel. So thank you for watching. Stay tuned. Hello all. In this section we are discussing the special pipe inspection tests which are generally there in aggressive environments. In this part we are going to discuss the hydrogen induced cracking. So let us start with the topic. So in this part what we are going to cover, in first section we are going to cover what is HIC, hydrogen induced cracking, why this type of cracking occurs, what are the various methods to test this, and we'll try to look at few pictures so that we can visualize what is happening when hydrogen induced cracking is there. First of all, let us try to understand what is hydrogen induced cracking. Right, it is just a definition. It is just a stepwise internal cracks that connect adjacent hydrogen blisters on different planes in the metal. Okay, if you look at these pictures, these are the examples of hydrogen induced cracking. It is generally a form of wet hydrogen sulfide cracking caused by blistering of metals, right, due to high concentration of hydrogen. This is the basic definition of hydrogen induced cracking. Mostly why it occurs? It occurs at low temperatures, largely as a result of atomic hydrogen from wet H2S corrosion reactions. Okay, this atomic hydrogen is forced to enter into the steel that are and collects at the inclusions or impurities within the steel. When this atomic hydrogen enters into the steel, it causes some cracks. These are called hydrogen induced cracking. Then H2S prevents hydrogen recombination. This is the basic reason why it occurs. This is the property of hydrogen sulfide which prevents hydrogen recombination reaction. That means bubbling of the corrosing surface occurs. The hydrogen atoms are forced into the metal structure, causing corrosion and weakness. Okay, H2S itself prevents the recombination reactions. That is why these are the atoms, hydrogen atoms, which are forced. Once these are forced, these enter into the surface, which causes corrosion and weakness. Now there are few tests which are available to identify these kind of cracking. Conventional method of detecting wet H2S cracking is wet fluorescent magnetic particle inspection, which is also called WFMPI, which is able to detect subsurface cracks in the steel caused by hydrogen induced cracking. When it comes to the cracked piping and other component which cannot be inspected using this testing inspection method, phased array ultrasonic testing is generally used, which is most convenient and reliable non-destructive testing method. So these are two methods which are generally used to identify this kind of hydrogen induced cracking. So in this part we tried to understand what is hydrogen induced cracking, why it occurs, what are the various methods, along with few of the pictures which are useful to visualize what is happening when this kind of hydrogen cracking occurs. In this video series we are discussing the special pipe inspection tests, especially in aggressive environments, and in this part we are going to cover the sulfide stress corrosion cracking. So let us start with the topic. Here these are the four parts which we are going to cover in this video. First one is what is sulfide stress cracking, second is when it occurs, what are the reasons behind this kind of cracking, then how we can prevent it. Okay, so let us start with the part 1. Now to understand what is sulfide stress cracking, we need to understand that this kind of cracking occurs where there is a tensile stress and corrosion in the presence of water and hydrogen sulfide, right? So this is the environment where this kind of cracking occurs. Tensile stress is there, and corrosion because of water and hydrogen sulfide. So these three elements will always be there when this occurs. So sulfide stress cracking is a form of hydrogen embrittlement, right? As we discussed in hydrogen induced cracking, similar effect is there, hydrogen embrittlement that occurs, but in this scenario it occurs only when there is a high strength steels, right? And it occurs localized hard zones. right? And again, when there is a environment which contains wet hydrogen sulfide. So this is what hydrogen sulfide stress cracking is. Now where it occurs, in most of the cases it occurs in iron alloys because of restricted slip capabilities in the predominantly body centered cubic structures. So when we are talking about where it occurs, you can say it occurs mostly in body centered cubic structures. Again, when those steels which are having hardness of 22 or greater on Rockwell C scale. So these two scenarios are there, when there is a hardness of this much scale and when there is a body centered cubical structure. Right, now let us see what are the causes when it occurs. Right, there exists synergetic effects of high yield strength and high H2S concentration in the environment. Right, as we have discussed earlier, we have two conditions: there should be high yield strength material and there will be a presence of H2S concentration. Right, it occurs it generally associated with welds, because when there is a heat affected zone and this kind of strength and this kind of concentration, these three combinations will cause the sulfide stress cracking. Now as we discussed, atomic hydrogen diffuses into the steel and causes embrittlement, especially in the hard zones, in the heat affected zones adjacent to the welds. So whenever there is a welding, there will be heat affected zone, and adjacent to those, if there are hard zones, then these kind of hydrogen embrittlement may occur in wet hydrogen sulfide environment. In the region of high tensile strength, there will be residual stresses available. Crack will initiate, leading to the crack propagation in the direction perpendicular to the tensile stress. So three conditions will be there: high tensile strength material, heat affected zone, and H2S environment. These three conditions when meet at single point, there will be hydrogen embrittlement which causes sulfide stress cracking. Now what are the various factors, how we can prevent it? We can control the stress level, right? The residual stresses we can remove, and we can control the hardness. Once we control these two factors, stress level and hardness, then there are less chances of this kind of environment. Also, if we apply the post weld heat treatment, then again this will reduce the level of stresses, residual stresses. Avoid the hydrogen source, we can keep our material away from hydrogen source, so there will be lesser hydrogen embrittlement. So these are few of the factors with the help of which we can we can prevent sulfide stress cracking. So in this part we discussed what is sulfide stress cracking, what are the various factors when it occurs, what are the various reasons behind it, and how we can prevent it. So this was all about sulfide stress cracking. Thank you for watching. So in this part where we are discussing the pipe inspection, testing and marking, in this particular specific section we checked about all the metallurgical testing, that is grain size, intergranular corrosion test, ferrite test, hydrogen induced cracking test, sulfide stress corrosion cracking. At the same time, if you look at various ASTM standards where we can get the chemical requirement, composition of various elements which are present in a particular steel, we can get those compositions, and with respect to that we can also refer these ASTM standards which talk about a lot of testing methods, testing requirements for a particular material. So those can also be referred in those particular material ASTM standards. So this was all about this section. So see you in the next part.